Hello, everyone. You're welcome to today's lecture. We'll be talking about the Wheatstone bridge and its applications. What do we mean by a Wheatstone bridge? A Wheatstone bridge is an arrangement of resistors that looks like what we have in this figure. We have 4 resistors, P, Q, R, and X. And the way the Wheatstone bridge operates is that in this scenario, P, R, and X are fixed resistors, while Q is a variable resistor. A variable resistor is a resistor that you can adjust its value. You can, or just like the common Aboki radio, you can increase the volume of the radio by turning its the knob gradually. That is what Q represents. That is what Q represents in this circuit. So Q is a variable resistor. P, R, and X are fixed resistors. In this arrangement, in the center here, we have a galvanometer G. Galvanometer helps in measuring current flow, tiny current flow. And when it is standing upright, it means there is no current flow. When it is deflecting to the left, let's say this way, that means current is flowing from the right to the left. And when it is deflected to the right, that means current is flowing from the left to the right. But once it is standing upright, that is like this, then we know that current is not flowing through the galvanometer. Then I would ask, what are the conditions that makes current to flow? Current flows when there is a variation in potential. So when the potential at point, just like we have seen here, when we close this key, so that this galvanometer will be able to measure the current flow from B to D, current will only flow if B and D are at different potentials. But once they are at the same potential, once point B and point D are at the same potential, current will not flow. Then the galvanometer will stand erect like this. And that implies that the term used in qualifying that is to say that the galvanometer, is to say that the Wheatstone bridge is balanced. The Wheatstone bridge is balanced when the galvanometer does not deflect. The Wheatstone bridge is balanced when the pointer of the galvanometer is upright. So just like I have here, the Wheatstone bridge is one of the electrical measuring devices operating on the principle of null measurements. It is often used to obtain accurate resistance measurements. So in this, one of the main applications of Wheatstone bridge is to determine unknown resistances. So when I close the keys, when I close key K2 and key K1, and the galvanometer, let's assume it is deflecting to the left, then I begin to adjust resistor Q because it's a variable resistor. I begin to adjust until the galvanometer stands upright, until the galvanometer stands the way it's standing upright, to indicate that there is no current flow between B and D, to indicate that there is, or that the potential at B is equal to the potential at D. So in that case, we'll be able to now read the value of resistor Q. And from the knowledge of resistor Q, we'll be able to determine the unknown resistor X. So if we know P, the value of resistor P and the value of resistor R, and we have a variable resistor that we can adjust such that we can vary the direction of current flow, either from left to right or from right to left, we can adjust Q such that we will get a balance where current will neither flow to the right nor to the left. From such balance, we'll be able to obtain the value of resistor X. So let's move along and see how it goes. So from this circuit, like it's written here, we assume that resistors P, R are fixed resistors with known values. Q is a variable resistor, which we can adjust its resistance, just like we are adjusting the volume of a transistor radio. And X is a fixed resistor of unknown value. So, and at the center, G is a sensitive galvanometer. So once these keys K1 and K2 are closed, once we close key K1 and K2, then we expect the galvanometer to deflect either to the right or to the left, depending on the direction of current flow. Then the variable resistor Q is now adjusted until the galvanometer stands upright, to imply that there is no current flow through the galvanometer. So I think I've said everything we have on this slide. So when there is no current flow through the galvanometer, we say that the bridge is balanced. The galvanometer bridge is balanced. Like I've said earlier, P, Q, and X are fixed resistors, while P, R, and X are fixed resistors, while Q is a variable resistor. You can see an arrow in between. So P, R, and X are fixed resistors. Q is a variable resistor, meaning that we can tune in like if you are increasing the volume or reducing the volume of a transistor radio. So like I said earlier, when we close this key, K1 and K2, and we adjust variable resistor Q such that there is no deflection on the galvanometer. At that point where there is no deflection, it means current is not flowing through the galvanometer. And it also means that the potential at point B, let's call it VB, is equal to the potential at point D. So VD, the potential at point B and D, when they are equal, we should not expect current to flow from B to D or from D to B. And in that case, when there is no current flow from B to D, it means that all the current that flows through P will flow through Q, while all the current that flows through R will flow through X. So from Kirchhoff's law, Kirchhoff's current law to be precise, we can call the current that flows out of the battery to be I. And the current that flows through P to be I1. The current that flows through R to be I2. If the bridge is balanced, that means I2 will still flow through X. If the bridge is balanced, I1, which flowed through P, will flow through Q. And I1 and I2 will meet at node C and flow back as I. And in this case, Kirchhoff's law tells us that I is equal to I1 plus I2. That is the algebraic sum of currents entering node A or entering node C is 0. And in this case, since point B and point D are at the same potential, then there will be no current flow either from B to D or D to B. Now we have assumed current I to flow through resistor P and I1 to flow through resistor P and current I2 to flow through resistor R. So let's move ahead. Recall that the potential, since we call this VB to be the potential at B and VD to be the potential at D, we can also call the potential at A VA. And we can also call the potential at C to be VC. Since we said the potential, when the bridge is balanced, let me clear the screen so that it will be a bit neater. When the keys are closed and Q has been adjusted such that there is no deflection on the galvanometer, meaning that the Wheatstone bridge is balanced, the potential at point B is equal to the potential at point D, VD. Let me make the D a bit smaller to look like V subscript D. Now we can say that the current that will flow through resistor P, the current that will flow through resistor P will be the potential difference across resistor P divided by the resistor P itself. And what is the potential difference across resistor P? That is VA minus VB divided by P. That will give us current I1 when the bridge is balanced. Similarly, we can say the current that will flow through resistor Q. So let me write it again. The potential difference across resistor P is VA minus VB. And the value of resistor P, let's call it P, is equal to, from Ohm's law, is equal to I1. And this I1 is also equal to the current that will flow through variable resistor Q. And how do we determine the current that will flow through variable resistor Q? Although it's I1, from Ohm's law, we can say the potential difference across resistor Q should be VB minus VC divided by Q. Similarly, we've spoken about the current through here to be I1. We can also talk about the current flowing through R to be I2, and also define it similarly to say VA minus VD divided by R equal to I2, and that is also equal to VD minus VC over the resistance of X. So the current that will flow through R, which is I2, is the potential difference VA minus VD divided by resistance R. Similarly, the current that will flow through resistor X is the potential difference across X, which is VD minus VC divided by resistance X. And when we remember that our VB is equal to VD, then we can come to this point and change all the, we can change the VD we have here. We can change them to VB. So by doing that, we can have our I1, we can cross multiply this expression to obtain I1, product of I1 and P. Okay, let me do it this way. Let's get a blank screen. Okay. So I1P will be equal to VA minus VB. So here we have replaced the VD here with VB. Then we can also say that VA minus VB divided by R times I2, equal to I2 rather. Then from here we can say I2R equal to VA minus VB. Since I1P is equal to VA minus VB and I2R equal to VA minus VB, then we can say that I1P is equal to I2R. So this is one expression we should put in our minds. And similarly, we would, just like we have treated the left hand side of this expression, we can also treat the right hand side similarly. Then we obtain I1Q to be equal to I2X. We can obtain I1Q to be equal to I2X. So this is another expression that we may find valuable for us. So let me clear the screen. Okay, coming back here. So these are the two expressions we had not long ago. I1P equal to I2R and I1Q equal to I2X. Then we can find I2 over I1 in both equations to be P over R we can find it to be P over R and also Q over X. Since P over R equal to I2 over I1 and Q over X equal to I2 over I1, then we don't need a prophet to tell us that P over R equal to Q over X. And if you want to make it a bit simpler, I prefer to have the formula written in blue as cross multiply. And I have P, product of P and X equal to product of Q and R. So P and X are opposites, the opposite side of the bridge, while Q and R are the opposite side of the bridge. So once the bridge is balanced, once the switches are closed, once the keys are closed, and the bridge is balanced, meaning that current is not flowing through the galvanometer, meaning that the potential at B is equal to the potential at D. Then we can say that the product of P and X, the product of resistance P and X is equal to the product of resistance Q and R. So a way this can be used, just like I've said earlier, is we know the value of P, we know the value of R, and we know Q to be a variable resistor that we can vary over a range. Then X will be, X being an unknown resistor, or a resistor with unknown resistance. We can obtain it by putting a galvanometer in between these points, setting Q until we have a balance. Then we know P, we know Q, then we read out the value of Q. Then using this equation, PQ as PX equal to QR, then we can determine the value of X. Okay, so I think everything over there is what I've said. Okay, so now we have an example. The example is saying we should calculate the value of X. This is a typical Wheatstone bridge. It is balanced. When we say it is balanced, it means when we close the keys, current will not flow. It means when we close the keys, or even when we open them, the potential at B is equal to the potential at D. I mean, the electric potential at B is equal to the electric potential at D, which implies when they are equal, which it implies there will be no current flow. So like the expression we had previously, and the formula I prefer, which says those that are opposites should give a product of the others that are also opposites. Now P is 10 ohms, X is unknown, Q is 20 ohms, R is 30 ohms, then X will be 20 times 30 divided by 10. And that should give us 60 ohms. So that is 60 ohms. So it means this 60 ohms. This is P is 10 ohms. R is 30 ohms. And Q is 20 ohms. So when you have the resistors arranged in this manner, 10 ohms, 30 ohms, 60 ohms, and 20 ohms, there will be no current between points B and D. The galvanometer will not deflect. if we decide to play with this a bit, let's try to play with this. We can replace, we can redraw this circuit to mean something like this. I hope I will find space here. Okay, let's redraw it 10, 30, 20, 60. Where you copy. $20, 60 ohms. Even as at now, we are less concerned with the value of the battery. And now we have the galvanometer connected here, and we are told that it is balanced. It is even balanced, even if we are not told. Let us try this. Circuit can be drawn in a way that is familiar to you. Where this will be 10 ohms, 30 ohms, 60 ohms, and 20 ohms. Let's write this one a bit more beautiful. If you want to simplify this circuit, you can come further to say these two resistors are in series, 10 and 20 are in series, and you replace with a single 30 ohms resistor, and you say 30 and 60 are also in series, and you replace them with another single 90 ohm resistor. Let's assume the voltage or the battery is, let's say 30 volts to make our life easier. Let's assume it's 30 volts. 30 volts means that the current that will flow through this 30 ohm resistor will be 30 over 30, 1 ampere. The current that will flow through this 90 ohm resistor will be 30 over 90. 30 over 90, that is 1 over 3 ampere. So that means that if you play after this class, by making 30 and 90 ohms, replacing them with a single resistor, resolving them in parallel, and the total current that will flow out of this 30 volt battery will be 1 over 3 ampere. Or better still, 4 over 3 amperes. So when 1 ampere flows through this channel, when 1 ampere flow through this channel, what it means is that, let me get another color. When 1 ampere flows, okay, I said after the class you can resolve these two resistors in parallel, replace with a single resistor, and then calculate the current that will flow out of this 30 volts battery, you would observe that the current that will flow out will be 1 ohm number, 1 over 3 amperes or 4 over 3 amperes. So now coming back to what I was saying, when we still maintain this to be 30 volts, and we said 1 ampere flows through the 30 ohm resistor, it means that 1 ampere will flow through the 10 ohm resistor and 20 ohm resistor. And when we say 1 over 3 ampere flows through the 90 ohm resistor, it means that 1 over 3 ampere will flow through the 30 ohms and the 60 ohms resistor. So now let's calculate what will be the voltage drop across each of the resistors. Since 1 ampere flows through this 10 ohm resistor, it means 10 volts will be dropped across it. 10 volts will be dropped across it. Since 1 ampere flows through the 20 ohm resistor, V is equal to IR. Initially, I said 1 ampere flows through the 10 ohm resistor. V is equal to IR. R is 10 ohms. I is 1 ampere. 1 times 10, 10 volts. In the second resistor, which is the 20 ohm resistor, it has a resistance value of 20 ohms. And the current 1 ampere flows through it. And that will give us 20 volts. That means 20 volts surrounding. And according to Kirchhoff's voltage law, you can see we have 30 volts as power supply, and we also have 10 plus 20 volts as voltage drop across resistors. So let's look at what will happen at the other set of resistors, that is 30 ohms and 60 ohms. In this case, a current of, in this route, let me use another color for that. In this route, a current of 1 over 3 ampere flows here, while we know that a current of 1 ampere the current here is that flows through this place is 1 ampere. So when 1 over 3 amperes flow through, so when 1 over 3 ampere flow through 30 ohms resistor, then the V equal to IR, our Ohm's law, will give us that the voltage that will drop will be current 1 over 3 times resistor 30 ohms, and that will mean 10 volts. So that means that 10 volts would, let me clean this place so that it will not look too messy. So that will mean the potential drop here will be 10 volts. While when this, when we want to know determine the voltage that will drop across the 60 ohm resistor, we can also say that V is equal to IR, just like we have said over and over and over and over again. The current is 1 over 3, and the resistance value is 60 amperes. 1 over 3 times 60 would have 20 volts. And that means that 20 volts will drop across the 60 ohm resistor. When we say this battery is 30 volts, it is easy to say that the potential at this point is 0, at the negative terminal is 0, while the potential at the positive terminal is 30 volts. When the potential here is 0, potential here is 30 volts, we can easily now check from this 0, what is the value at this points. What is the value at this point? That means the potential at this point, looking at what we have just calculated, that is 20 volts. And when we look at the potential at this point, looking from what we have just calculated, it is also 20 volts. That means that current will not flow from this point to this point, which means that when you connect a wire there, current will not flow through the wire. When you connect a galvanometer there, current will not flow through the wire. The current through this channel is 1/3 ampere, while the current through this channel is 1 ampere. According to Kirchhoff's current law, 1 ampere here plus 1/3 ampere here will add up to give us one whole number, 1/3 ampere, that will flow back to the battery. And the same one whole number, 1/3 ampere, is what flowed out of the positive terminal of the battery. So one whole number, that's my pen again, one whole number, 1/3 ampere, flowed out of the battery. It got to this terminal. It considered the resistance of this point. It's noticed that this is a total of 30 ohms. This is total of 90 ohms. This is posing great resistance compared to this channel. So that means that larger current will flow through the channel of low resistance, while smaller current will flow through the channel of high resistance. That is why 1 ampere decided to flow through this channel, and 1/3 ampere decided to flow through the channel. According to Kirchhoff's law, the current that flowed into this junction must be equal to the current that will flow out of the junction. That's Kirchhoff's law. And according to Kirchhoff's law, the current that flows into this junction from both ends will be equal to the current that will flow out of the junction. So I hope I've shed more light on Wheatstone bridge, Ohm's law, Kirchhoff's law. So to continue, let's talk about the meter bridge. The meter bridge looks like the Wheatstone bridge, just like we have a resistor. Sorry. Just like we have resistor P, Q, R, and X in Wheatstone bridge, we also have, in this case, this is like a metal conductor. So this is not a resistor. F to H is a metal conductor. K to B is a metal conductor. And between A and B is a meter of wire. It's a meter of high resistance wire, usually Constantine wire, the wire you find on the meter bridge in the laboratory. So the length, if it's a meter bridge, that means it is 1 meter, and 1 meter is 100 centimeters. So when you have 1 meter, it means that if you take your L1 to be 40 centimeters, then you surely know that L2 will be 100 minus 40. So when you know L1, you definitely know L2. When L1 is at 10 centimeter mark of the meter rule, then L2 will be taking the remaining 90 centimeters of the meter rule. So just like I don't know if we have said this before, but one of the properties of resistance and wires is that the resistance of a wire, let me get a color blue. The resistance of a wire, let's say R, is directly proportional to the length of the wire. So the longer the wire, the larger the resistance. The longer the wire, the larger the resistance. So that means that we can split A and B into two with this galvanometer to say that from this point B, we have set up this resistor P, resistor Q, and another resistor of length AB. We can now try to determine that at what point on this wire, will have the same potential as we have in between P and Q. At what point on this wire will have the same potential as we have between resistors P and Q. So before we think about the galvanometer, we should think about the fact that we have connected this battery across these two resistors. These two resistors are in series with each other. And these two resistors are in parallel with another resistor here. And as we'll be saying in the next topic, voltage is dropped across A to B. Let's say, for instance, this battery is rated 12 volts. This is the negative terminal. We can call this potential 0. I will call this potential of 12 volts. That means that at this point B, it will have potential of 0, and at point A, it will have potential of 12 volts. And that means that when you measure the voltage from point B to any other point on the wire, it will be increasing from B to A. That means that the potential in this wire AB is a resistance wire. The potential at any point AB increases from B to A. In fact, B is 0 and A is the potential of the battery. So that means that we can have any potential value, we can find any potential that is needed on this wire between A and B. We can find any potential we desire on this wire. So by moving from 0, 0.1, 0.2, get to 1, to 1.5, to 2, 3, it will keep increasing until it gets to 12. Between P and Q, it's a potential. The potential here too is 12. The potential at the end of Q is also 0. But what is the potential between P and Q? What is the potential between P and Q? We can connect a galvanometer at this point, just like we did in Wheatstone Bridge, and begin to move the jockey all around from A to B, back to A, until the galvanometer shows 0 deflection. When we slide it upwards here, we should expect this to be a very high potential, higher than this point, let's call it point G. We would expect the galvanometer to deflect to the right because currents will flow from this point to point G. When we slide the jockey close to B, we would expect the galvanometer to turn the opposite direction because currents will flow from from G to the point C. Okay, let me take that again. Let's take 2 points here. Let's call this point C1, which is having a potential that is greater than G. And let's take another point C2, which is having a potential that is lower than G. When you take this jockey at C, when you bring it to C1, currents will flow from C1 to E. Current will flow from C1 to E. And the galvanometer will deflect to the right. But when you bring it to, when you bring the jockey to point C2, current will flow from G to C2, making the galvanometer deflect to the opposite direction. But there is a particular point C where there will be no deflection. There is a particular point C whose potential is equal to the potential we have at point G. At that point C, where it is called the balance point. It is the point where current will not flow through the galvanometer, and we can say that the bridge is balanced. This time, not Wheatstone bridge, but the meter bridge. And we should always remember that the longer the wire, the larger the resistance. And the length of the wire in this scenario, L1 plus L2, will always give us 100 centimeters. That means when we know L1, 100 minus L1 will give us L2. And if we want to talk about constant of proportionality here, I know for the sake of knowledge, the resistance of a wire is directly proportional to the length and inversely proportional to the cross-sectional area. And there is a constant of proportionality rho, which is the resistivity. And that leads us to say that R is equal to rho L over A. But in this case, A is uniform. A is the wire, the constantan wire, or the resistance wire. A is uniform, so we are less concerned about A. And since it's the same material, we are even less concerned about the resistivity of the wire. What is of interest to us is the resistance of the wire is directly proportional to the length. And when we bring in constant of proportionality, we say R equal to KL. Then we can come to say K is equal to R over L. And we can proceed to say that R1 over L1 equal to R2 over L2. And we can still continue to say that L2 is equal to 100 minus L1. So let's move forward. Okay, so okay, that's goes to another topic. Moving forward, we can say that the product of the resistance P, because like I told you in the while talking about Wheatstone bridge, the formula of interest is to say that the products of opposite resistance, in this case, P is opposite the resistance RCB. P times RCB is equal to, and the opposite ones here as well, we have Q times RAC. P times RCB equal to Q times RAC. Then we can say P over Q. We can say P over Q is equal to RCB. Sorry, I wanted to say RAC divided by RCB. P over Q equal to RAC over RCB. And what is RAC? Going by the concepts of resistivity, RAC is L1 and RCB is L2. So we can say RAC over RCB equal to L1 over L2. Since they are directly related, then we can just come here to say P over Q equal to RAC over RCB, then L1 over L2. You can make things simpler by, instead of saying L2, to say L1 divided by 100 minus L1. Then to put it in a simple summary, we can say P over Q equal to L1 divided by 100 minus L1. So the clause is that L1 is measured in centimeters. That's the clause. And the length of the wire is 100 centimeters. That is 1 meter, where we get the name meter bridge. So let's see. Let's see what next. So in the next class, we'll be talking about potentiometer and its applications. Potentiometer are very similar to the idea behind potentiometers is very similar to what we have discussed in this class. So we'll be talking about them on Thursday. Let me go through the chat box. I think there are some questions. Okay, talking about Kirchhoff's law. We went through Kirchhoff's law in the last class, and I have made some videos that I would publish from 12 noon today. I think about 6 of them. I'll publish them every hour all through today, from 12 p.m. every hour. So if you, it will be on my YouTube channel for you to watch, just for sake of those that did not get it completely, because there are many examples on Kirchhoff's law. We can continue to go on, and we would run out of time. So I've made them for you to watch and rewatch, and I think you'll find them useful. Let me see. There is a question here says that, sir, please, since the current is moving from left to right, why not VB minus VA, not VA minus VB? VA is having a high potential there. That is why I chose to take VA minus VB, because VA is connected directly to the positive terminal of the battery, while VB is midway, all the way towards the negative terminal. And the current, I'm concerned about the potential difference across that resistor and the value of that resistor, that is the resistance of the resistor, and the current that will flow through that resistor, and that is potential difference over resistance will be current flow. That's Ohm's law. So can we also say that the potential as A is the same as at potential at C? Potential at A, let me quickly look at where is A, where is C? No, potential at A is not equal to potential at C. Potential at C is even ground, it's 0. It is connected to the negative terminal of the battery. So we can't say that. Potential at A is connected to the positive terminal. So they are not the same. It's only potential at B that is equal to the potential at D when the bridge is balanced, when you have adjusted resistor Q such that the potential at B will now be equal to that of D. Let me look again if we have some other things we can. What do we intend to achieve by setting up the meter bridge? Okay, what we intend to achieve is to determine the value of an unknown resistance. So in the meter bridge, we may know P, we don't know Q. We know P, we don't know Q. So, but let me quickly run there. We know P. We know the value of P. Let me clear the screen. We know the value of P, but we don't know the value of Q. But we know the length L. Since we know the length L1, we know the length L2, we can use that to determine the value of Q after we have balanced the bridge. I think there are more questions coming in. Our time is running out. How do we recognize the positive and negative terminal of the meter bridge? The negative terminal of the meter bridge is connected to the negative terminal of the battery is 0. The positive terminal is the long parts of the battery. You can see there are parallel lines, but some are longer than the others. The long ones are the long part is the positive terminal, while the short part is the negative terminal. How do we know the current is flowing from left to right or right to left? Current flows only when there is potential difference. Current flows only when there is potential difference. Can you make a video to explain Wheatstone bridge more exclusively, sir? Okay, I'll try to do something on that. But I think the video of this lecture will be put online as well, which you can note the period where I've discussed Wheatstone bridge. I think I've exhausted the main questions here, and I've put some slides on the LMS, and this lecture video will be uploaded later on within the day, and also the videos. I've made some videos that I said I'll be publishing from 12 p.m. today. So every hour they'll be on my YouTube channel. So we'll meet on Thursday.